Recall that the main goal of our series is to find a description for the set of primes that a polynomial f split over. In the case when f was not abelian, the most that we could have said so far was about the size of split f. On the other hand, when f is abelian, we can actually say a lot more. It turns out that when f is abelian, i.e. if its Galois group is abelian, then split f can be given by a congruence condition. This turns out to be if and only if, and recall that we have already proven one direction of this. We have shown that if split f can be given by a congruence condition, then Q of f must be an abelian extension of Q. Recall that we proved that using the fact that split f uniquely determine the splitting field of f. And thus if split f is given by a congruence condition, then Q of f must lie inside some cyclotomic field, and it must therefore be abelian. Now let us look at the other direction. Let us suppose that Q of f is an abelian extension of Q. Why would this imply anything about split f? Or more generally, what is the relationship between the Galois group of f and the set of primes that f split over? So Artin actually found an explicit description of this relationship. For an abelian extension K of Q, he constructed a map that associates to most prime of Q an element of the Galois group of K over Q. What is this element? Well, it's the Frobenius map at P. Roughly speaking, we can think of it as the lift of the Frobenius map on finite field. The idea is that if we have a rational prime Q, and suppose that Q factor in OK in the following way, then for any prime beta here in this factorization, we'll have that OK over beta is going to be a finite extension of FQ. Its Galois group must therefore be cyclic, generated by the Qth power map, which is the Frobenius Q map. It turns out that when Q is unramified in K, we can always lift this map on quotient to a map on OK and then to an element of the Galois group. It's going to be a well-defined element if this Galois group is abelian. In this case, we call this lift the Frobenius Q map. If you want to know more details, you can check out our video on the Frobenius elements. And so the Artin map associates to unramified primes in K the Frobenius element Frob P. This is an element of the Galois group of K over Q. Now how does this relate to splitting? Now it turns out that when K is the splitting field of a polynomial f with integer coefficient, then the kernel of this Artin map is just gonna be, roughly speaking, the set of primes that f split over. This is gonna be true for all but finitely many such primes. This is because of the following. So let's say we have an unramified rational prime P. This just means that the extension of P into OK factor into a product of distinct prime ideals. There is no multiplicity in this factorization. Now by Chinese remainder theorem, we know then that we have the following factorization of this quotient OK over POK. On the other hand, for most P, this quotient is going to be isomorphic to the quotient of fpx over fx. This means that f split completely in this fp, so f split completely modulo p, say into x minus alpha 1 dot x minus alpha r, if and only if this quotient here is isomorphic to a product of fp. That again is by Chinese remainder theorem. Now then, that happens if and only if each of these quotient here is isomorphic to fp. In other words, f split completely modulo p if and only if each of these quotient is a trivial extension over fp. And that's the same as saying that the Galois group of this extension is trivial. But remember, the Galois group of this extension, as we've mentioned, is cyclic, generated by the Frobenius element. So this extension is trivial if and only if the Frobenius element is trivial. Thus, f split completely modulo p if and only if Frobenius p is trivial, i.e. if and only p lies in the kernel of the Artin map. So that is how the Artin map relates to splitting. Now, so what is this kernel? This is answered by the ultimate reciprocity law, Artin reciprocity. Why is it called reciprocity law? Well, because it describes the kernel and the image of the Artin map. And as we have said, the kernel of the Artin map describes the set of primes that F split over. Hence, any description of this kernel is a reciprocity law. For now, let's just be hand-wavy and say that this kernel can be given by a congruence condition. And so coming back to our Abelian polynomial theorem, we then see now that if the splitting field of F is abelian over Q, then split F, being the kernel of the Artin map, can be given by a congruence condition. Well, okay, this sounds a little bit like cheating, but the purpose of these videos are just for giving a taste. You know, it's like a teaser. If you want to know the nitty-gritty, you can look at our more detailed videos on class field theory. So that concludes our discussion on what a reciprocity law is. We saw that in the case when f is an abelian polynomial with integer coefficient, then we can get a reciprocity law, i.e. a description of split f in terms of a congruence condition. The reason is because in that case, we can think of most rational primes of Q as an element of the Galois group of F. This is done via the Artin map, which associates to each such prime a Frobenius element. Now then, in that case, the split primes of F are just, roughly speaking, the kernel of the Artin map. And by Artin reciprocity, this kernel can be given by a congruence condition. Thus, when F is abelian, i.e. when the splitting field of F is an abelian extension of Q, split F can be given by a congruence condition. When F is not abelian, though, the most that we can say is about the size of split F, i.e. the density of split F. This is a content of the Weak-Chebutarev's theorem, which is a consequence of the Chebutarev density theorem. The Chebutarev density theorem gives us the size of the fiber of the Artin map. It is a generalization of Dirichlet's theorem for primes in arithmetic progressions. Thus, in our discussion, we've had a glimpse of three themes of class field theory, namely abelian extensions of Q, reciprocity laws, and density theorems. This series definitely did not do justice to this beautiful theory, so I hope that you get a chance to explore more of this in the future.